Okay, let's get started. The past decade has been really, really exciting for machine learning because we've gotten systems that can actually work. They can make predictions fairly reliably, fairly accurately in a number of domains. I think the next frontier of AI is going to be systems that actually interact with the world. They can optimize sequences of actions. That's what reinforcement learning is all about. It's about creating sequences of actions that lead to good outcomes. It's about improving through experience. The work that I've done throughout my PhD casts reinforcement learning as a sort of probabilistic machine learning problem. And in today's talk, I'm going to talk about why that's been useful. It's been useful because it's made it easier for users to use these reinforcement learning tools, to specify outcomes. I can just give examples of those outcomes. But more than that, this idea has also led to better algorithms that not only outperform prior methods, but also can find patterns and structure in the solution to decision-making problems. And that's what I'm going to talk about today, the work that we've done in the thesis, and how some of this work might enable certain potential applications of reinforcement learning. Reinforcement learning has the potential to unlock applications in nearly every aspect of our lives. A lot of the foundational work in reinforcement learning is in games like Go or Atari or poker. But the potential applications are much, much broader. They include things like robotics, robots that help patients in hospitals, robots that safely drive our cars, robots that make our warehouses safer. Problems like robotics are really hard. This robot here, it has 20 motors, one in each knuckle. How should you control those motors? What sequence of commands do you show them so that you eventually solve this Rubik's Cube? There are potential applications in our built world too. How can we optimize the sequence of traffic lights so we spend less time sitting at intersections? And how can we do this making use of large streams of data that flow into centralized centers in major US cities? In healthcare, AI systems are already being used to help predict the outcomes for certain patients. But maybe the next set of AI tools will actually assist physicians in making decisions. Applications in robotics and healthcare, they require learning from historical data. We don't want to be learning by trial and error. There are potential applications in education too. We've seen the blossoming enrollment in CS classes. How can we leverage that to figure out what sequence of problems to show students? How should those problems depend on students' past experiences? And in the sciences, conventional machine learning tools might be able to predict the outcome of some experiment. But reinforcement learning tools, they may allow us to dynamically control those experiments. Of course, all these potential applications, they're not going to be solved with reinforcement learning people alone, but in collaboration with domain experts in concert with other areas of machine learning. But I think that reinforcement learning is a really important piece of this puzzle because reinforcement learning, it lets us optimize for the long-term outcomes. Most of the successes that we've seen in reinforcement learning have been in the context of games. And I think the reason why is that we know the rules of games. We can simulate games. We can generate lots and lots of data. But the progress in other applications has been a lot more measured. And I think the reason why is that it's a lot harder to get the data, and it's a lot harder to give feedback in these other applications. And so if we hope to make progress on these potential applications, we're going to need a way of developing reinforcement learning algorithms that can learn with less feedback. And in today's talk, I'm going to talk about the work that we've done in the thesis towards this end. First, how we've made it easier for users to give feedback by just giving examples of good outcomes. And second, about how we've developed algorithms that can infer structure in the solution to decision-making problems, breaking down hard problems into easier problems that we can learn with less feedback. So to start, to make sure we're all on the same page, I want to briefly review how the reinforcement learning problem works. On the left here, I'm showing a robot task, and this is what I'll refer to as the environment. There's this robot here, and to control this robot, we're going to take the action to respond to opening and closing the robot's hand, moving the robot hand to the left or to the right. And we observe observations.
I'll see you guys.
observations in this setting are going to correspond to an image, showing us the pixels, what's happening in this environment right now. And the most important object is this policy down here that allows us to figure out what actions do we take given the current observation, given this current state S. And at the end of the day is this policy that we want to learn. And we're going to learn the policy by using these rewards here. The rewards say, is this a good state or is this a bad state? And we want to find the policy that takes us to states that are good not only now, but also lead us to good states in the future. This reinforcement learning problem is really exciting because it's so general. All of those potential applications of reinforcement learning that we saw, those are examples of this problem. But this generality also makes it really hard. And I want to review what I think is the main challenge in reinforcement learning. I think the main challenge is the lack of feedback. And I want to review what I mean by this. In reinforcement learning, maybe we have this robot here, we want to pick up this block. And it takes 1, 2, 3, 4, maybe 5 actions. And at the end, they get some feedback saying, okay, you've gotten to some good state. You get this reward of this +5. But before then, the robot might not get any feedback. And this is very different from supervised learning, where for every input, you get the feedback, you get the label. And this problem is compounded by the fact that we want to solve reinforcement learning problems in high-dimensional settings. Those observations, those images, to a computer, they just look like a big block of numbers. And the reason why looking at high-dimensional problems is important is because it's precisely on these high-dimensional problems that we expect learning-based approaches to outperform classical approaches. And there's a third problem, too, with providing the feedback, a practical challenge. Why should this state here get a reward of +5? Well, in practice, it was because a bunch of grad students spent too many hours writing this big block of code here that says, okay, when you're at this state, you get a reward of +5. But this big block of code, it serves as a barrier to entry. How many users would like to apply reinforcement learning to their problem, but don't know how to write a big block of code like that? And even experts might look at this and say, is this correct? Will this result in the desired behavior? And as we move to real world problems, even running this piece of code is hard. Say this piece of code here, it requires knowing the positions of every object in the scene. But even the best object detectors we have, they sometimes make errors. And so if you hope to make, and so if we hope to make progress in reinforcement learning, we're going to need a way of learning from less feedback. Now, these problems of learning from limited feedback with high-dimensional data are new to reinforcement learning. And in fact, we've seen similar problems in other areas of machine learning. And there, in domains like computer vision and natural language processing, we've seen how self-supervised approaches have achieved really excellent results. And so I want to review how those methods work. In computer vision, there are methods that say take an image and cover up pixels of that image or patches of that image and try to predict what those missing pixels or patches are. And these are the techniques that underlie some of the generative AI models that you may have seen over the last year. Similarly, in natural language processing, there are methods that take a sentence and cover up the words of that sentence, and then try to predict what are those missing words or what is the next word of that sentence. And these are some of the techniques that underlie some of the large language models that you've probably seen over the last year. And there's another class of self-supervised methods. These are contrastive learning methods, methods that look at the inputs and try to learn the representations so that similar inputs have similar representations. And it's these last class of methods that we're going to build upon today. So these self-supervised methods in other domains, they've achieved really excellent results, learning from high-dimensional data with limited feedback. How can we realize those same gains in the reinforcement learning setting? What does it even mean to do self-supervised reinforcement learning? If I had to summarize my thesis in 5 words, it would probably be this: that we've just started to lay a foundation for self-supervised reinforcement learning. And in today's talk, I hope to give you a taste of what this means. How we've developed practical algorithms that we actually can implement and actually run in the real world. Theoretical guarantees for these methods, that allow us to answer questions about when and where we expect these methods to work. And also uncovering certain connections between these reinforcement learning methods and other areas of computer science, and even other areas of machine learning too. For folks on Zoom, if you wouldn't mind muting, that would be fantastic. Thanks. Okay, so here's what I'm going to talk about in today's talk. I'm first going to talk about how we can learn goal-reaching skills. These goal-reaching skills are going to unlock a couple capabilities. First, they're going to allow users to specify tasks by just giving an image of what they would like to happen. They no longer need to write that big block of code that we saw before. I'll talk about how we've deployed some of these methods in the real world in collaboration with folks. And then I'll talk about some of the theoretical properties we've proven about these methods, connecting them to reward maximization in a way that actually allows us to expand them and apply them to fully general reinforcement learning problems. Not only are these goal-reaching skills useful in their own right, but they also will provide the right abstraction for planning. And by incorporating these skills into planning algorithms, we'll be able to extend their capabilities by over an order of magnitude. And doing this will allow us to apply these methods to this outdoor robot shown here. Now, of course, when we want to apply reinforcement learning to real-world problems, ensuring that our methods are robust is really, really important. And we've studied robustness in a number of ways. We've looked at how regularization can provide a certain degree of robustness. We've looked at how to make use of approximate models, learning from them while recognizing the errors. But I'm not going to talk about our work on robustness and generalization today. So to get started, I want to talk about this first part, about learning these goal-reaching skills. And I'm going to start by defining the problem statement. This problem of goal-conditioned reinforcement learning. So let's say we have this robot that I started the talk with, and we want this robot to pick up the green object, move it into the blue bin. Well, we could write down that big, complicated reward function we saw before. But instead, we're going to ask the users to just provide an image of what we would like the robot to do. What is the desired outcome? So in this case, the desired outcome, to get there, we would want the robot to go down and grasp the green object, pick it up, move it over a little bit to the blue bin, and drop it into the blue bin. This problem of goal-conditioned reinforcement learning is actually a very old problem. And some of the early work in AI, including work right over there from NSH, was on this problem of learning goal-reaching behaviors. Now, we're going to study this problem in a particular setting, one where we're given as input a data set. In this set, it'll be a data set of videos labeled with actions. And one thing to note is that these videos, they're not necessarily optimal. The actions in them are not necessarily good actions. But from this data, we're going to try to find skills that can reach goals as quickly as possible. So why is this problem useful? Well, practically, it's going to make it easier for users to specify tasks. But mathematically, it's also going to build upon the prior work and allowing us to apply these methods to settings that have continuous states and observations and actions, as well as problems with stochastic dynamics, while retaining certain theoretical properties. We'll show that this maximizes a well-defined objective. So how are we going to do this? How are we going to learn these goal-reaching skills? Well, we're going to do this in two steps. The first step is going to entail learning representations from these data. And learning representations is important whenever we're dealing with high-dimensional data. And then the second step is going to be to learn these goal-reaching skills from these representations. So that's the game plan. And I'm going to start by talking about how we learn these representations. So there are many prior approaches you could use for learning representations of high-dimensional data. There's some methods that look at the frames in a video and try to predict what is the next frame in the video. There are other methods that say look at the frames individually in some video and try to learn some representation that tells you about the contents of that frame. What these methods typically don't do is they typically don't tell you about the actions. They don't tell you, well, if you wanted to get from point A to point B, what actions should you take? And so we're going to need a different way of learning the representations. Our method for doing this is going to build upon prior methods developed in the computer vision and natural language processing community, but we're going to extend it to the reinforcement learning setting. And that's this idea of contrastive learning. And I want to walk you through how we've applied this to the reinforcement learning setting. We're going to learn two representations, a representation of the states and the actions, as well as a representation of the future states. And we're going to do this using the data set of the videos and the actions. So to start, we're going to take a video, and we're going to take two images from that video and say these images should have similar representations. And precisely, these two images are going to be sampled so they're a certain distance apart from each other, a distance governed by a certain geometric distribution. So they're most likely to be 1 or 2 steps apart, but they could be 3 or 4 or more steps apart. And that geometric distribution will be important for proving certain theoretical properties of these methods. And then we're going to look at a second video. And we're going to say that images from different videos should have different representations. And so what's the intuition here? The intuition is that these representations, once they're learned, they should tell you something about the difficulty of getting from one state to another state. If the states have similar representations, it's pretty likely you can get from one to the other. And importantly, these representations, they depend on the action. And that was the key property that was missing from some of the prior methods. So I want to show you an example of what these sorts of representations they learn. So we did this by applying these methods to the simulated manipulation task here. And in this task, there's this robot arm, there's this red object you can move, there's this drawer you could open if the red object moved. And we can think about these representations as points, but we're going to normalize these points so they lie on a sphere. This is a common technique. And now, the way that we were learning these representations was by looking at the distance between them, precisely by looking at the dot product between these representations. And so one way of thinking about these representations is that they're encoding a sort of model of the world, but one that predicts not what is the future observation going to look like, but what is the representation of some future state going to look like. These are the representations. They also have very strong connections with some classical ideas in reinforcement learning relating to successor features and successor representations. And I can talk more about that at the end. So if we look at these representations and look along this path here, we can visualize what our method learns. And I want to point out two things about these visualizations. And these visualizations, they were created using a nearest neighbor retrieval. So the first thing to note is that all these images have the same contents as this observation and the final observation. They all have the red object and the green object. But more than that, they also seem to have captured some notion of physics. So if you notice, this red object here, it only moves when it's being touched. And similarly, this drawer, it only moves when the robot arm goes down and touches it. And this is different from what prior methods would do. If we take a different method, a common deep learning method known as a variational autoencoder, and visualize its representations, these representations, they capture the contents of the scene, but not the physics. You notice that the arm moves, but it never touches the objects, even though the objects are also moving. And so these representations and these visualizations of them, they gave us some hints that, well, maybe these are the right representations to use for building those goal-reaching skills. Because at the end of the day, these representations were motivated by learning these goal-reaching skills. And so I want to walk you through how we then learn these goal-reaching skills from these representations. And I'm going to use an example, that same robot task I showed at the beginning. So let's consider two actions, one action that moves the block to the right and one that moves it to the left. And if you recall, the really important property of our representations was that they depended on the action. And so action 1 has one representation and action 2 has one representation. And we can look at the distances between these representations and the goal state. And based just on these representations, do you folks think we should take action 1 or action 2?
2.
Yeah, so we can see, okay, action 2, it has a representation that's closer towards the goal. And so that's probably the action we should take. And that's exactly what we do. We define each skill as simply taking the actions whose representations are closest towards the goal representation. So just to summarize this, we started with this data set of the videos and the actions. We then learned these representations, and then we extracted the skills, those goal-reaching skills, from these representations. Now, at this point, we can use these skills to solve certain tasks. We also could use these skills to go back and collect some more data. And we've shown that these skills work in both settings. Now, to provide a bit of context here, I started this section by talking about why reinforcement learning is hard. It's hard because of the limited feedback. And ordinarily, we think about reinforcement learning as requiring a fair number of rewards to learn. But we often think about goal-conditioned reinforcement learning as an even more challenging problem. Because if learning how to reach one goal required one reward function, maybe learning how to reach many goals requires many reward functions. But what we've seen here is that we can cast this problem of goal-conditioned reinforcement learning in an entirely self-supervised way, such that we can learn these goal-reaching skills without ever having to specify a reward function. No user had to come write that big block of red code that we saw before. And I think this can help explain why these methods can work well. And so after showing these methods, they work well in simulation. Together with collaborators, we looked at applying these methods to a real-world manipulation task. This robot shown here is a Widow X robot. It's a small, low-cost robot, which makes it pretty accessible, but also pretty finicky to work with. And I want to show you the skill that we learned for trying to get to this goal state shown here. And the difference between the starting state and this goal state is that the red spoon has moved to the left. And from a robotics perspective, this task is fairly challenging because we're going to do the learning from suboptimal data. It's not going to all be demonstrations. We don't know the positions of all the objects. We're doing this directly from the images. And we're going to learn this without ever interacting with this environment. There's not going to be any trial and errors, all learned from that pre-existing data set. And just to underscore the difficulty of this, I want to show you what a prior method does. The prior method moves the robot arm to the correct position, but it never goes down and grabs the red spoon. And in contrast, here's our method. We see that the robot arm, it goes out of its way to grab that red spoon, drop it on the left side, and then move the hand up. Now, one property of these goal-reaching skills is really important, is that they were learned without any particular goal in mind. They were learned just from that data set, which means that if we want to solve some different task, for example, if we wanted the robot to push a can across a table, the only thing we need to do is give it a new goal image. We don't need to do any more training. We don't need to do any more gradient updates or specify any more data. And so without using that exact same policy, but giving it a different goal, we see that the method is able to push the can across the table. So I hope these results, they help underscore the practical utility of these sorts of methods, that we can learn purely from the historical data, that no users had to specify those reward functions. And the way we did that was by first learning these representations and then using these representations to extract the skills. Now, from a theoretical perspective, there still remains a pretty important question, which is these skills, how do they relate to reward maximization? Reinforcement learning, it's built upon this foundation of maximizing rewards, but do those skills, those goal-reaching skills, do those actually maximize any sort of reward? We'll see that answering this question, showing that these skills solve a certain type of reinforcement learning problem, helps us extend these methods, applying similar techniques to fully general reinforcement learning methods. And to provide a little bit more context here, these self-supervised methods upon which we've built, in other domains, there's often a disconnect between whatever representations you're learning and whatever downstream task you're trying to solve. But we'll see that in the reinforcement learning setting, there ends up being a very close connection between the representations you've learned and how you use those representations in the setting to solve decision-making problems. So here's our main theoretical result. Our main theoretical result is that these representations, they tell you about the future returns. Precisely, if you look at the dot product or the similarity between these representations, this tells you about the rewards that you'll get in the future. And precisely, these rewards here are a very natural reward function, one that says, okay, do you get to the goal at the next time step? But importantly, we never have to actually compute those rewards there. One thing I should mention is that this reinforcement learning objective on the right-hand side is about maximizing probabilities, trying to get to the goal with the highest probability. But it has very strong connections to a different objective, trying to minimize the total number of steps required to get to a goal. And so just to visualize this result, when we were defining these skills, we were looking at these representations. And what this theoretical result says is that when we were looking at the distances between the representations, that was not a heuristic. That was a principled thing to do. And similarly, when we were choosing the actions based on which action got us closest towards the goal representation, that too was a principled thing to do. And I should also mention that we've extended these results so that we can reason about what representations you would learn if you had applied these methods to a different data set, a data set that had been collected by a different policy. And so what this theoretical result means is that those skills that we showed before, those were solving a certain type of reinforcement learning problem, reinforcement learning problems with these goal-reaching rewards. But this connection, it also has enabled us to extend these methods to apply them to fully general reinforcement learning problems. And one way we've done this is by giving multiple examples of outcomes, where the probability of an outcome corresponds to how much reward you would like to have. So just to summarize the section here, we started by talking about how users no longer need to specify these rewards. They can instead just give examples of what the desired outcomes look like, giving one goal state or many goal states. And these skills, they can be learned both in the interactive setting or in the setting where we're learning just from an existing data set. And finally, we've shown how there are certain connections between these goal-reaching skills and reward maximization. Now, one thing I should mention is that these goal-reaching skills that we've learned, they're not magic. And so we tried applying these methods to this task shown here. This is a 3D simulated house. And there's a robot that walks around this house. It has a camera. And we give the robot an image of where in the house we would like it to go, and we see whether it gets there. And what we see is that if the goal is in the same room as the robot, then the robot succeeds in reaching that image. But if the image is in a different room, then the robot typically fails in reaching that image. Now, on the one hand, this is not that surprising. If you think about the number of action sequences of length, say 20, that number of sequences is astronomically large. But it turns out the components we've learned so far, these representations and these goal-reaching skills, they can allow us to solve even the most distant problem, even the most distant goal, if we incorporate them into a planning algorithm. And that's the next thing I want to talk about today, how these goal-reaching skills provide the right abstraction for planning. So historically, there have been two ways that people have thought about solving decision-making problems. The first part of this talk focused on learning-based methods, methods that learn directly from the raw data. But there's another class of methods, planning methods. These methods are really powerful. This is what a lot of the early work in AI was about. And this is a lot of the technology that underlies the internet, how the information on my laptop is getting to everyone's laptops on Zoom. Now, what planning methods require is they require a symbolic representation of the world. Now, what they lack, though, is they don't have a way of taking raw high-dimensional data and converting that into symbols, converting high-dimensional data into some graph. And it turns out that these self-supervised reinforcement learning methods that we've seen, they can provide the right abstractions for applying planning methods to high-dimensional data. And so I want to show you how that works. In the earlier part of this talk, we talked about how we can use data, this data set of videos and actions, and use that to learn these goal-reaching skills as well as these representations. And so we're going to start by applying that method to a data set collected from that simulated 3D house that we failed to navigate before. And now we're going to use these components to build a graph, because a graph is what planning methods require. We're going to build a graph in the following way. The nodes of this graph are going to be frames taken from these videos, sampled uniformly at random. And the edges of this graph are going to be built using these representations that we've learned. And for visual clarity, I'm going to ignore edges that would be too long for showing this graph. And now that we have this graph, we can apply planning methods to it. So let's say we want to navigate from one image to another image on distant corners of this house. Well, we can plug these images into this graph and then find the shortest path on this graph. And now we can use those goal-reaching skills that we've learned to traverse the edges of this graph. So we take the first image along this path, and we use these goal-reaching skill to take a sequence of actions to get us to that first waypoint. And then we repeat this process. This method I've outlined here, it also can be entirely reinterpreted in a probabilistic way, where we're trying to infer what is the sequence of states you would visit if you navigated from one state to another state. And I can talk more about that at the end if folks are interested. I want to walk you through an example of how this works. So we evaluated the method on a number of goals. Here's one example where the robot starts seeing this image and wants to navigate into this kitchen shown here. And here are the sequence of images that the method inferred. These are the images it thinks it can visit when it's navigating the house, going closer towards this cupboard, going to the kitchen, and then going towards the stove up there. And if we take a bird's eye view, we can see that these images actually make a lot of sense. They correspond to almost the shortest path through this house. This bird's eye view is something we use just for visualization. The robot doesn't actually get this bird's eye view. And quantitatively, we see that while those goal-reaching skills on their own fail to solve the distant tasks, by incorporating them into a planning method, they can successfully reach the most distant goals, succeeding over 95% of the time. After showing these results in simulation, we worked with collaborators to apply these methods to this outdoor robot shown here. We gave an image of where we wanted it to go. My fantastic collaborator, Drew, who led this effort, put a pizza on top of the robot, because you see, this robot was given a picture of the customer's door. And so it could autonomously and in a contact-free way drop off the pizza at the customer's door. This was in the middle of COVID, so contact-free pizza delivery was a very pressing problem for grad students. These methods of combining learning and planning, there's since been a lot of follow-up work that's extended the capabilities and lifted the limitations of these methods, making them more robust, making them generalized more broadly. And to provide a bit of context here, in AI very broadly, there's been a long discussion about should we prefer planning methods or should we reason about symbols or learning methods that can learn directly from the raw data. And one reason I'm excited about this effort here is that it provides one recipe for combining these two components together. And so the takeaway from the second part of this talk is that these skills that we've learned using these self-supervised methods, they provide the right abstraction for doing planning. Now, taking a step even further back, I started this talk by mentioning why reinforcement learning is hard. It's hard because of the limited feedback. But what we've seen today is that we can learn goal-reaching skills without any rewards, without any feedback. And we can compose these skills to solve challenging tasks. So I hope this has given you at least a little taste of some of the work in the thesis, which I would encourage folks to go read, about how we've developed practical algorithms, theoretical guarantees for those methods, as well as uncovering certain connections between reinforcement learning methods and machine learning methods and some other areas of computer science. And the work that I've done, it informs a lot of the work I'm excited to do moving forward. So practically, the next step is I will be joining Princeton in the fall. And there are a lot of research questions that I'm really excited to study with students there. First and foremost, there are some really exciting questions at the intersection of reinforcement learning and natural language processing. over the last few years, and even over the last few months, we've seen some really impressive results from big AI models that can reason about both images and language. What these methods typically lack is a grounded understanding of the world. In contrast, the methods that I've developed, they can reason about actions and interacting with the world and images, but they don't yet have an understanding of language, of semantics. How can we combine these two components together, getting the strengths of both of them? Well, it turns out the theoretical foundations of both these methods are the same. They're both built on top of contrastive learning methods. And so I think there might be some really elegant ways of bringing them together. And in the same way that we've shown already how we can learn goal-reaching skills that can navigate to a goal image, maybe now we can learn language-reaching skills that can infer the sequence of actions to get to some language in the future. Or in the same way that the second part of this talk looked at inferring a sequence of steps to get to some distant goal, maybe now we can infer the sequence of language instructions required to solve some challenging task. Second, a lot of the work that we've done, and the work I highlighted in the second part of this talk, is about finding structure. It's about breaking down challenging problems into easier problems. Now, the second part of this talk, I showed how we could say, given two images, infer the sequence of images that you would visit between those two images. But can we take this a step further? Can we, for example, learn skills that interact with the representations? Or can we learn skills that interact with other skills? The results I've shown already extend the capabilities of skill learning methods by about an order of magnitude. And if adding a layer to this hierarchy, if every layer extends the capabilities by another order of magnitude, maybe now we can start solving tasks that are well, well beyond the capabilities of today's methods. We have some preliminary work showing how this might be done. And I think that we might also be able to build upon some fantastic older work on hierarchical Bayesian modeling. And then there's certain theoretical reasons why these methods might be better suited to the reinforcement learning problem. Because in reinforcement learning, you can dynamically change your data distribution. Third, and finally, the work that I've talked about today, there's really strong connections with generative modeling. Generative models, they too are learned just from raw data. Given in a sentence, like a castle in the mountains, they can give you an image of what that castle looks like. When we view reinforcement learning as a generative problem, we now get the recipe for building that castle. Of course, actually figuring out how you would solve a problem as challenging as this, that's a really, really hard problem. It likely is going to require learning from very large amounts of data. It likely is going to require the right representations, the right sort of abstractions. But these are all problems that we've started to make progress on. I think this making progress here, it may unlock certain applications in gaming and creativity, but also in the physical sciences. In the sciences today, generative models are already widely used, say, for optimizing molecules. And when we view these problems as reinforcement learning problems, now we might get the recipe for actually running those experiments. Of course, this too is a very challenging problem, but I think that some of the work we've done might be useful towards this end. Some of the work on robustness and generalization that I didn't talk about today, it tells you how you can make use of approximate models, which is really common in scientific applications. The work that I did talk about learning directly from the outcomes, I think that might be directly applicable, because now we might be able to provide just examples of what the outcome of some experiment might look like. So I'm going to wrap up the future work right here. And I want to take a second to thank the fantastic team of collaborators, not just here at CMU, but at Berkeley and at other schools throughout the US, North America, and even around the world. Thanks. And I want to give a special thank you to my advisors, Sergey and Russ, for reading through hundreds or thousands of pages of notes and half-brained papers that never ended up seeing the light of day, for sitting through and critiquing, giving feedback on hundreds of harebrained ideas, the vast majority of which didn't work out, but a very, very small fraction of which turned into the work that you saw today. and of the hundreds or thousands of emails and Slack messages for keeping the research on track. Thank you.
Thanks, Ben. So we're going to start with the questions. And I guess we're probably going to go with the most remote right now. That would be, well, technically that would be Sergey, but we'll go with Leslie. Leslie, do you have any questions?
Sure. So thank you, Ben. That was good and interesting, nicely presented. Yeah, so let's see. I have questions at the high level and the low level. Let's take some high level ones, right? Which is one thing that you talked about that I thought was interesting is, you know, we could it's exciting to be able to learn from offline gathered data. And in particular, you had, I think, combinations of like images and then robot actions. And I was thinking, have you played around with trying to extract, in some sense, the robot actions from the videos? In your cases, you could mostly see the robot moving around. So that would be latent, but you'd have pretty good information about it. Is that something that you have thought about?
So to make sure I understand, the problem setting will be one where we're given just the videos without the actions and try to learn from that.
But where the actions were kind of not totally hidden in the video so that you could probably recover them.
It's really funny you mentioned that, because just yesterday, I scribbled all over my whiteboard some proposals for how we could do that. And so there's an ongoing Slack discussion exactly about a very related question about how we can take action-free videos and then infer skills from that action-free video, those action-free videos. And I think that some of these techniques about inferring structure might be useful there.
Yeah. Okay, that's cool. So one more thing is, and in your final, you know, kind of future work also touched on it, but I have, since we've begun talking, and in particular talking about goals.
Yeah.
For me, you know, a goal is a set. You know, am I in my office or not, kind of. And so using images as goals, it's interesting because it's both under and over specified in a way, right? It's a little too specific because here it is, this particular image, and it's a little too general, maybe because there's some parts of what matters to me that I can't see.
Yeah.
So what about broadening what you take to be a goal?
So one way we've done this already in one context, and then I think there's some exciting directions looking at going forward. One way we've looked at this already is by this extension of the goal reaching problems, where we gave multiple examples. And the aim here is that each goal image individually is definitely overspecified, in that when we want a robot to pick up an object, we might not care what color, what shape that object is. We just want it to pick it up. Or when we want a robot to clean some bedroom, we don't care the order in which it stacks the books on top of the coffee table. We just care that they end up stacked there. And the aim is that by providing multiple examples of good outcomes, in the same way that an image classifier can see multiple examples of cats and say, okay, this is what a cat is, that our methods might be able to know, okay, this is what success looks like.
Well, I'm curious then, there's now a technical point, which is, if you're going to be goal conditioned, how do you manage that if the goal is articulated in the set of a large set of images?
Yeah, great question. So the work that I'm referring to here, the policies that are learned are not goal conditioned. They take as input just as state, and then take the actions that try to lead to these goals. But the critic, the way they're inferring whether the actions will lead to good outcomes, those look at, okay, the likelihood of getting to one outcome, the likelihood of getting to another outcome. And you probably can imagine how you can use this to estimate likelihood of getting to any or at least one outcome.
Sure. Yeah. Okay, good. I get it. All right. I think I'll pass the baton.
So maybe go with Sergey.
Sure. So in the beginning, or towards the beginning, you had this nice illustration of how representation is learned with contrastive RL compared to like VAEs and things like that. And you made this point that if you interpolate, you kind of get these nice in-between frames. That seems interesting, but my question is, why do you think it matters to have a representation that's metric in that way?
I don't think that linear interpolation is necessarily what we want, but I think the property that we really want is we want to be able to do planning. And so when we looked at those representations, and I'll try to pull up the example of them. Here, planning, if we wanted to figure out what intermediate images would look like, if you wanted to get from one observation to another observation, would just correspond to taking the average of these representations. And this is really important because if we want to solve long horizon tasks, breaking them into easier smaller, easier tasks would be useful. But as long as there's some easy way to do planning using the representations, I think that's sufficient. And so I don't think we necessarily need to have this linear interpolation property. In fact, I think it very likely will harm us.
Well, okay, but just to push on this a little bit more, like, if you want to do planning, let's say you want to do some like tree-based thing, all you really need is a way to like propose successors or evaluate if a potential state is a successor to a given state. Like none of that really says anything about what the representation should be. It just says that, well, that there needs to be a good model available. So do you think that there's some relationship between the representation and the model, and does the geometric structure of the representation in particular matter? Like, I guess that's what I'm not seeing is like, well, what's the link between geometric structure and planning in this case that you're trying to articulate?
The geometric structure allows us to solve planning, gives us a closed form solution for planning. Another way we could do planning is by actually learning a planner, something that takes as input a state and a goal and predicts what some intermediate states would look like or some next state looks like. I think there's a spectrum of methods based on how much representation learning they do, and then how much model learning they do. And in some sense, we've pushed really far to one extreme where all of the horsepower is going into learning the representations, and then the model learning drops out immediately from that. And we could imagine methods that spend more computation on doing the planning and a bit less on learning the representations. What's the right trade-off? I don't know. I think there's very likely methods sort of more in the middle that we haven't explored yet. But I think it's interesting to explore the extremes to see, well, to explore the extremes, because if we can solve the entire planning problem with the representations, then that might provide a recipe that us as academics can really benefit from. Because now we could offload the big, large representation learning problem to collaborators in industry. And then we might be able to very easily use the representations learned to actually solve the planning problems.
Okay, yeah, that makes sense. I guess my other question is, you know, if we think of these things as good representation learning methods, then kind of the obvious question to ask is, well, can we do what people always do with representation learning methods and train them on the largest like internet data set that we can get our hands on? I know this is something you've thought about a lot, but I guess my question is, what do you think are the bottlenecks that you'd start to hit if you were to try to do that?
I think one bottleneck is that internet scale data is incredibly broad, but perhaps not very deep. And one way I sometimes think about the reinforcement learning problem is that it's sort of like solving a supervised learning in every separate situation. So it's solving many of these problems. And if we don't have that many examples for any individual problem setting, then even though we might have data for millions or billions of problems, if we don't have enough data for any of them, then it might be hard to make progress. And so one of the things that I think would be really useful is trying to figure out how we can collect a similar quantity of data, but in a much more limited setting. I know this very much goes against the grain of what a lot of folks are excited about in terms of learning just from YouTube or just from the Twitter or Reddit. But I think that for the reinforcement learning setting, it might be really important for at least making some initial steps towards understanding how much data you need to see certain emergent properties on even relatively restricted domains.
Okay, yeah, that makes sense. That's it for my questions.
Thank you, Jeff.
Great. Let's see. I'll start maybe with a kind of a low-level question. Can you go to slide 13? Let's see. Yeah. So I think the idea here is that you want an encoding that will make a state and action pair end up with almost the same encoding as a future state, right, by itself. And then that's the basis of what happens after that. My question is, doesn't this have a weird side effect with very stochastic actions, that actions that have two very different outcomes, this will force two very different outcomes to actually end up with an almost identical encoding, when in fact those two very different outcomes it might be important that they don't get the same encoding. Is that a potential problem? Does that, yeah, are stochastic actions generally more of a challenge with this approach?
I haven't applied this to stochastic action, so I can't give an empirical answer. I
Okay.
agree that from a theoretical perspective, it seems like this will work better in settings with deterministic actions. The theory holds regardless of whether it's stochastic or deterministic. We can show that the inner product corresponds to a value function. But I don't think I can imagine that sort of capturing that multimodality could increase sample efficiency, for example. Because in some sense, what we're trying to do is we're trying to learn an incredibly complex representation such that once you have these representations, the prediction problem is trivial. But the prediction problem is often not trivial if you have possible stochastic outcomes. And so having a bit more expressive model that says, okay, given the current representation, predict the future representation, that might allow you to learn much simpler representations.
So let me see. I'm trying to understand. Are you arguing that that you should try this algorithm on problems with stochastic actions and maybe good things happen anyway? Or are you arguing that, well, maybe we can make some adaptations to the algorithm that'll make it perform better with stochastic actions? Or are you arguing that if you have a problem with stochastic actions, you haven't really formulated the problem correctly? You should re-ask what your state and action space is and make it a deterministic problem.
I'm definitely not saying the third. I think
Okay,
that there's
okay.
many real world problems that have stochastic actions, and
Okay.
those fit very nicely into the MDP framework upon which we built. So I think that's fine. I think you definitely should try these methods on settings with stochastic actions. I think they very likely will work. The point I was trying to make is that learning these representations might be challenging from a function approximation perspective.
Yeah.
Dynamics in the real world are very, very nonlinear. What effectively this is saying is that the representations there's a way of showing that this corresponds to learning a linear model of the world. And so you sort of have to untangle the complexity of the world, the fact that dynamics are not reversible, the things that breaking things is not reversible, such that you get representations where things are linear. So it's a very, very complicated mapping. And if we don't have function approximators that could represent that complexity, then part of the way of dealing with that limitation of existing function approximators would be to use a more expressive mapping from one representation to another.
Okay. Good. I think I want to ask another version of the question Leslie asked. My version of the question is, what about distractors? So, you had the picture of the moving the spoon to the other side, but what if it's just a different colored table? And it would be very hard to figure out how to swap out the table, but presumably you'd still want it to realize it just needs to move the spoon to the other side. How do you, in practice, how do you actually get that similarity right?
I think that's a really important question. I brought up this slide because this slide shows a similar failure mode. If you look very carefully, you'll notice that the rotation of the can is actually different between the two images. And so how do we learn representations that capture just what we want and what we don't want? I haven't looked at this problem in particular. I think there are techniques relating to compression that might be useful here. Saying we want representations that not only predict the future, but retain as few bits as possible about the inputs. I think techniques relating to data augmentation might also be useful. But I think it's still a largely open question.
Yeah, I guess compression, you could certainly look at compression techniques, but one thing that's missing in your training data, you don't actually have any notion of which differences matter. Right, I guess a lot of compression algorithms have some version of entropy or reconstruction or something that's kind of generic.
Yeah.
But I guess you would actually need that extra signal, I guess.
Absolutely, yeah. If
Right.
someone gave us a bunch of images and said, hey, you should think about all of these things as the same. You should think about pushing a green can and a red can and a purple can. Those are all the same task. Collapse all of those together. And if we had data like that, then I definitely think there'd be many ways that we could incorporate it into these sorts of frameworks.
Okay. And I have a question that's maybe related to that. Can you scroll back to maybe slide 23? So this one went kind of fast. You said IQL failed here.
Yeah.
What's the setup here? What actually happened with? So this is the same setup you have. You showed her a bunch of videos, things moving around different places.
Yeah. So it's a really interesting failure mode.
Yeah.
I did gloss over this. So the failure mode is that there are two things that are different between the initial image and the goal image. The first thing that's different is the red spoon moves.
Yeah.
And the second thing that's different is that the robot arm moves. Yeah. And what this baseline does is it solves one of those problems. It moves the arm to the correct position. Mm-hmm. And my hypothesis for why this happens is that the arm occupies more of the image than the spoon. And so it's stuck in a bit of a local optima. Now, why would our methods help avoid that? Well, we can think about the training dynamics of these contrastive methods. What they're doing is they say, okay, look at these representations, look at the future, the images in the future, and say those should have similar representations. And then look at not one, but many, many other representations and push those away. That's what standard contrastive learning does.
Yeah.
But if you look at the gradients there, what it effectively is doing is finding the closest negative example and pushing that away. And so I don't think we're the first to observe this, but the training dynamics of contrastive learning methods resembles a form of hard negative mining. It induces a sort of curriculum. And we have some analysis showing how that happens, but I think it helps explain why it fails, because in the learning, there should it should be able to find counterexamples where the arm is there and it says, okay, that is not the state that you would reach if you wanted to pick up the spoon.
Okay. Maybe one more question. So I guess in the work you've done so far, you're, I guess, assuming the exploration problem is kind of solved for you.
Yeah.
The training data covers what you needed to
Yeah.
cover. Have you thought at all about whether your methods say anything about better exploration or what you would do for those kinds of problems?
Yeah, so the skill learning methods I talked about at the beginning were these goal reaching skills. Mm-hmm. The mathematical foundation of them is based on these sort of contrastive learning and mutual information ideas. And we've actually applied at the very start of my PhD, I started using very similar ideas to actually derive a method for exploration. So I can pull up one video of that, of using very similar mathematical tools for learning skills here that are not oriented towards any particular goal, but just trying to explore the environment. So this is definitely not the end-all be-all solution. There's been a lot of great subsequent work that's extended these methods and so on. But I think that there might be some ways of using similar self-supervised methods to not only learn the representations, learn how to do the planning, but also help drive the exploration.
Good. I'm good.
Just have one question, maybe just to follow up on Jeff's question, is that when these methods fail, does it usually sort of comes from, especially like, this representation, like does it usually come from not enough coverage of the data? So for example, let's say you've never seen spoons in the training, but you've seen a lot of other things and you're moving, you're learning those representations. Would you be able to move spoons, or do you think that there's, just trying to see like how much is there sort of like a notion of the coverage that you need to learn these representations and how well they would do on new objects and new things we generalized that.
In the simulated setting, we studied this a little bit. So we showed, for example, that if you train on one color table, but you evaluate on a different color table, then it will fail. But you can perturb things to a smaller extent, like change just the colors of objects. And then these methods tend to still work. In terms of evaluating on things that are entirely outside the data distribution, we tried this for one task on that real world robotic manipulation task. I think it was picking up a plastic baguette. And I believe that it failed on that task. So we just
is it because of perception, or is it because it just doesn't recognize what it is, or Or is there something else going on?
I'm not entirely sure. We haven't probed whether it's the representation learning or the choosing the actions based on those representations. I think that for a lot of these things, looking at bigger and bigger data sets will likely help. But developing high fidelity simulators might be really important there because it will allow us, it will tell us how much data we need to expect certain sorts of results.
The reason why I'm asking is that I think that most recent sort of foundation models for computer vision, like, they're becoming really good at like segmenting things and such. And it seems to be there are some cases where learning policies in the simulator while applying them in the real world with some of these strong sort of perception models, they actually beginning to work reasonably well. So yeah. So that's why I was curious, like how well you can actually take these models and apply them in the real world in new sort of settings. Is it provided the perception is actually doing the right thing?
Yeah, that's a really good point. We haven't looked. I guess one thing that talk about a bit about is when I talked about the foundation models here, I was focusing on language. We could imagine using very similar methods for just leveraging like large video data sets. And we learn the representations of large videos that would tell you not only about the contents of the videos, but also something about the dynamics of the videos.
Right.
Like if we think about I think historically the thing that has made reinforcement learning benchmarks hard is that they have lots of visual complexity, but the actual control problem is often very easy. But I think that might change over the next 5-10 years. We might see benchmarks where solving the perception problem becomes relatively easy, but solving the planning problem becomes a lot more challenging. And to tackle that sort of problem, I think that learning from what videos tell you is what could happen in the future. They don't tell you how to make that happen. That would require inferring the actions or reasoning about what would actually take you from one frame to the next frame, getting back to Leslie's earlier question. But they might tell us one way of incorporating the large foundation models into these sort of self-supervised methods.
Any questions from the audience? Waiting and yes.
Could you go over the intuition as to why VAE doesn't learn the physics of the scene, but the contrastive method does?
So this has to do with how the representations are learned. So the VAE that's learned here is learned in static images. And so the VAE has never seen what could happen from one image to the next image.
So is there no way you could put in like temporal dependencies into the VAE to try to get it to learn the physics?
Yeah, you could imagine applying a sequential version of a VAE, a sequential VAE. This isn't standard practice for reinforcement learning benchmarks. But there's been a little bit of work there and we could try doing that. Yeah.
Like, isn't that what like green algorithm does? Basically like a sequential VAE. So I'm just curious like what the contrastive learning part gives you that sequential VAE.
I think there are two parts that it gives us. One is that it aligns the model or the representation learning part with the downstream task. So if we think about just fitting a model of the world, something that predicts the next image or the next representation of the image, based on reconstruction, there's no guarantees that the bits that were useful there are the same bits that are going to be useful for selecting the actions. Very likely the bits that are important are like, what are the colors of the object? But that might not matter for solving certain control problems.
Okay, so I think that actually kind of gets a bit to Jeff's distractor question too, because it sounds like the contrastive method might be more robust to distractors.
It will retain different bits of information. So bits of information it will ignore are bits that have nothing to do with that are uncontrollable, but are persistent across episodes. And so what's an example of this? If the object positions just disappeared randomly across time, like there's like a noisy TV in the background or something, there's no temporal correlation, it would ignore that. But it's not perfect, and I don't want to claim like, oh, this is the panacea that you all should be using, because this method will pay attention to things like the background color. If every episode has a different background color, because the way these representations are learned are saying, okay, are these two images nearby in the same video? But one easy cue for that would be, well, if different videos have different colors, then you could sort of cheat by picking up on that. And so in theory, they still work in those sorts of settings, but in practice, I imagine that you might need much more data to learn in those sorts of settings.
Thanks.
Any other questions from the audience?
And we got a question from the Zoom audience.
Oh, yeah, okay, well, we can take on Zoom, and then maybe just one more, and then we'll.
Yeah, go ahead and.
Cool, sweet. Oh, awesome. Yeah, cool. Okay, so great talk. I have a question around like what are your thoughts on like this, you know, there appears to be like this trade-off between having feature-rich representations on the one hand, and then like interpretability and sample efficiency, right? So it's almost like there's like some trade-off there. So like, you know, towards pushing increasing sample efficiency, it seems like we might have to go for feature representations that aren't as interpretable. So I mean that's like a claim, but like, yeah, just curious to get your thoughts on like those 3 dimensions.
Yeah, I'll talk about the interpretability part first. So I think the representations we learn, they give us a certain sort of interpretability. The interpretability they give us is the likelihood that you get from one state to another state. And I think that interpretability might be useful in a number of ways. Already we've shown how it's useful for driving the selection of actions. So it's okay, these are the good actions to take. But you could imagine it would also be useful for understanding where methods are likely to fail. For example, if you have a bunch of observations that you know are bad, you can use these representations to figure out the likelihood that you would ever visit those bad representations. One thing that's kind of weird here is that very often when we think about interpretability, we think about the coordinates of the representations. So you might look at the representations learned by some deep neural network and say, oh, this coordinate corresponds to class representing dogs, and this coordinate corresponds to tree leaves. But what the representations here are doing is the coordinates individually might not be interpretable, but the inner product between representations is the scalar quantity that might become interpretable, because that tells you the likelihood that you might visit, say, a state that has a tree leaf in it. So I think they're just trade-offs.
Cool, thanks.
Okay, so maybe we can quickly go over the second round. Leslie, do you have any more questions?
Leslie, I think you might be muted.
Yeah, a train was going by, so okay. I saw something tantalizing on slide 40, but I didn't get a chance to look at it. Something about generalization, which is one of my favorite things.
Yes.
Oh, broader generalization, right? Okay, so, okay, I had just a tiny bit of a bad reaction to the idea that planning can only happen once you have a graph, because there's lots of work that happens planning that doesn't necessarily involve creating a graph.
Yeah.
But what I was really thinking about when I heard you talk about this, which is super cool, like I like the idea of kind of coming up with this structure and kind of understanding what you can do locally and then patching that together. But I'm really concerned about generalization, and in particular, like, how could we take learning to navigate in this one house and use it to help navigate in another house? So what are your thoughts about that?
We tried this.
Okay.
And there is a slide where we talk about it. Okay, so we tried this in the following setting. We said, if you learn in one house, there's definitely no way that you would be able to navigate in different houses. That's just unrealistic. But what if we try to learn those same 2 components, that those representations or that value function and the policy in not one, but many, many houses?
But wait, can I ask a question first? Like, it doesn't even make sense, I think, or maybe you're going to tell me it does. If I take an image from your house and an image from my house and ask about the dot product, what is that? What is that about?
Yeah, so the way we did this was we made one assumption that's perhaps non-standard. So the assumption we said is that when you're in a new house, you're given a small number of images from that house, not videos, but images, upon which you can build this graph. And then you use that value function and the policy you've learned in the training houses to build a graph on these small number of images from the new house and traverse between these images.
Interesting. So do you have a sense of what has to be? I mean, this clearly kind of wouldn't work all the time, but I can see how it would work some of the time. Do you have a kind of a concise way of describing when you think it would work and when it wouldn't?
Yes, my understanding is that for it to work, we need the value function to give us reasonable estimates between states, and for the policy to give us reasonable estimates for the best action to select given the current state and goal state. And I think now we're looking at what looks to be a much more standard machine learning problem, where if we think about viewing both of these as standard machine learning problems, then it's just a question of, well, are the testing houses in the distribution of training houses? And as we make the data set of training houses and testing houses larger and larger and assume that they're drawn IID from the same underlying distribution over houses, then I think it might be reasonable to expect that sort of generalization.
But let me just test my understanding for 1 second, right? So imagine that in my house, it's like, I don't know, the kitchen is right next to the front door. And in your house, it's a giant mansion and the kitchen is miles away from the front door. Then the value function for kitchen to front door is going to be pretty different. And the more houses we average that over, the kind of less good it's going to be in specific. Or am I missing a way to condition on the house?
This is a really good point. So I think you're right that the performance is going to be a lot lower. And we also found this in practice, that the difficult tasks, we're solving half of them, not 100% of them. And I think there was likely bias in how this distribution of our houses was created. And so there was kitchens were often maybe next to bathrooms and fridges were in kitchens. I think that to solve fully general problems, we would actually want to incorporate exploration into this, to think about, well, given this graph, how do we visit every node on this graph while also biasing us towards the high likelihood nodes? I think it's got to Jeff's point earlier. Together with my collaborator, Drew, who I mentioned before, we've explored this a little bit in the outdoor navigation setting. But I think there's still lots of open questions.
Yeah, I mean, I think probably you'd want a hierarchical model in the end, right? You wanted to revert to what you know about houses in general until you've explored this one a little more and then somehow let that take over. But yeah. Okay, good. Next.
Okay, do you have any more questions?
Yeah, I actually wanted to push on some points that are maybe related to what Leslie brought up. Is I think that's something you're kind of sweeping under the rug with the SORB example, and I think this to some degree is present in the other tasks, but is especially visible here. Is that you're sort of shoehorning partially observed problems into a fully observed formulation. And I wonder if you have any thoughts, like if you were to actually approach this properly as a partially observed problem, how do you think the methodology would need to change?
So there's the trivial answer, which is, well, if you incorporate all the past history, then the partially observed problems become fully observed. But I think that's complicated by two things: practical things and are relating to architectures and stochasticity. So the first is actually taking into account the whole past history is going to be really hard in terms of like, how do we could shove that into whatever newest transformer we have, but that might require very, very long contexts. So I think there might be certain ways of, so one way we could imagine approaching this is by learning models that for varying lengths of context and seeing at what context length do these methods actually start getting reasonable performance. And hopefully we would see that, okay, performance is low for a small context, but then increases at around a context length of 10, then you're able to solve tasks reasonably well. There's also this problem of stochasticity, which is a little bit subtle, but I think that when we think about partially observed tasks and map them onto MDPs by including history, they are going to likely be much more stochastic than the tasks we ordinarily think about solving. And I think it's possible that probabilistic methods might work a lot better in those sorts of settings. If we think about because we need to exactly reason about, say, the likelihood or the probability of something happening in the future, but integrating out all of the intermediate outcomes. And we've seen exactly how ignoring that stochasticity can cause problems for other sorts of reinforcement learning methods, in particular ones based on conditional supervised learning.
Yeah, that makes sense. For what it's worth, I don't think that the idea of shoving into a giant transformer and just using that as your representation is that terrible, but yeah, good answer. I don't have any other questions.
I'm debating whether I have another question. I was just thinking about the new houses problem and just trying to figure out whether when you go into a new house, you need a fundamentally different strategy because you're not you're not really even learning to navigate. You're just doing exploration. You're trying to find the bathroom, whatever. And you're just running an exploration algorithm. Maybe it's biased a little bit by where you usually see these things in other houses. I'm just trying to understand whether I believe the answer is you're just running a completely different policy and maybe you should be training a completely different policy. Or whether the answer is when you go in a new house, you actually run your policy as if it were in the training data, but you're adding the new data you collect as you go, and that works. It converges somehow.
I think it's really
I don't know if
interesting.
there's a question there, but I'm just filming what I was thinking while you were talking.
Yeah, I think that's really interesting. Exactly what I was going to mention seems related to Leslie's points about hierarchical designs being useful, because the low level motor control problem is very likely going to be the same. But the high level problem, it might not. Before I was talking about solving a shortest path problem on this graph, but maybe now you want to solve some sort of traveling salesman problem or some sort of vehicle routing problem on this graph.
It's a little bit of a different problem.
I don't know.
Maybe just one more question from the audience and then.
So, if you're solving the problem in a continuous space, so how would you behave in a discrete space where you might end up in a solution that space of solutions? How would you test it?
By discrete space of solutions, are you thinking about the observations?
Special discrete space. Actions.
Yeah, we've looked at discrete actions in a couple. I don't think I showed any results for it here. But the mathematical tools end up being the same. The difference is that when you're extracting the skills, you just consider a discrete number of skills. So actually, this slide actually makes a lot more sense in the setting with discrete actions. So you could enumerate, say you have 4 actions, look at the representations and choose the best one. And continuous actions, we actually did a form of amortized optimization for learning the corresponding policy here.
Okay, so then maybe we should, there are no more questions. Thank you, Ben. We're gonna keep everybody out and everybody on Zoom as well. So. We can ask people to, you have a way of keeping people out as well, right?
And I'm going to stop the recording.
Yeah.